So today we will discuss this topic, that is reduced switch count, multi-level inverter topologies. Right. So before that, we need to see the drawbacks of that conventional multi-level inverters. So that is this diode clamp multi-level inverters, flying capacitor multi-level inverter, and this is cascade H-bridge multi-level inverters. The main drawback for these devices are switch count. Okay. The switch count is, for example, this NPH, all these required 2 into M-1 switches, and this additionally it requires clamping diodes, whereas this flying capacitor require these flying capacitors, so these capacitor circuits. So all these things make the circuit bulky when we increase the number of levels. For example, same thing, if you are increasing it to 7 level, right? So how many you require? So 6 into 5. Okay, so 6 into 5 is roughly around 30, right? So this is only for one phase. In case of 3 phase, you require 90 diodes. So these are the drawbacks of this conventional multi-level inverter. So to overcome these drawbacks, we have this reduced switch count multi-level inverters. So the idea of this is to obtain a multi-level output waveform with reduced number of switching devices, right? So the reduced number of switching devices means either reduction in switches, right, like IGBT reduction or diode reduction, or DC source reduction IGBT, diode, or DC source. This is the latest, these are the whatever we discussed right now are the latest inventions. So these reduced switch count multi-level inverters are developed based on these constraint factors. So one, the main objective is to reduce the device switch count and reduce the device blocking voltage and make the structure more modular. So modular means if you want to increase the number of levels, we can easily do that. So that means if earlier we have 5 level, if you want to make it 7 level, right, so just by adding another unit, so you can make it to 7 level. And fault tolerant ability, so whenever some faultage occurs, the inverter is to reconfigure and still it will operate with the same capacity or with some derated capacity. And distribution and utilization of DC sources. Okay, so whatever the DC sources that present in the inverter, so that must exhibit the same power. Voltage balancing and self-balancing ability, in case if you are using a capacitor, right, so that must be self-balanced. And nature of the DC link and requirement of bidirectional switches and reduction in switching losses and conduction losses. So these are the main motivational factors so that we are using to reduce the switch count. So based on that, so we have different types of inverters are available. So one is the symmetrical and asymmetrical topologies. So we already discussed, right? What is symmetrical? When you have the DC sources all are same, so that topology is symmetrical. So when you have a different ratio of DC sources, so that is asymmetrical. With separate level and polarity generator, so we'll discuss now. So with H-bridge and hexagonal switch cell topologies, HSC means hexagonal switch cells topologies, that also we'll discuss. So with modular and redundant structure, the structure must be modular and it must be redundant. So meaning of redundant is to obtain a one voltage level, we must have several options to obtain. That means several switching paths must be present to obtain a single voltage level. So with equal blocking voltages, so that means the blocking voltages of switches as far as it must be equal. So it must be unit based. We'll discuss this, what is unit based. Topologies with bidirectional switches. So far the discussed topologies, that is CHB or flying capacitor or this diode clamped, so these are normally known as conventional multi-level inverters. So those are of unidirectional switches, but now these topologies may have these bidirectional switches also. Topologies with floating and isolated DC sources. For CHB you require isolated DC sources, right? So topologies with series parallel DC sources that we will discuss shortly. So these are the main classification of these reduced switch count multi-level inverters. So we'll start with the separate level and polarity generators. We'll start with level and polarity generators. The first one is there are several things are there, means several topologies are there in this. So first one is MLDCL, multi-level DC link. So this is SSPS, switched series parallel sources. So this is SCSS, series connected switched sources. So this is reverse voltage, and this is multi-level module, and this is crisscross topology. These are all comes under the separate level and polarity generator. Right. So we'll discuss one by one. We have other topologies, right? We will come back to this. Right. So this one is the first one. So that is multi-level DC link. Multi-level DC link. It's also known as MLDCL. So this is the circuit topology for the MLDCL. The circuit is consists of two parts. So one is the level generator and other one is the polarity generator. Okay. So the level generator, the name indicates it will generate the levels. Okay, it will generate the levels. So each level generator consists of this kind of off-bridge cells. This is an off-bridge cell, right? So this is also known as chopper cell or off-bridge cell. The circuit will be something like this. So we have a DC source. So across the DC source, and here you have another switch. So we are measuring output across this. This DC source is Vs. If this switch, for example, this S1, this is S1 and this is S2, we are measuring voltage between A and 0 here, right? If S1 is on, the voltage across A and 0 is Vs. If this S2 is on, the voltage across A and 0 is 0. Right. So that means it will produce two levels, Vs and 0. So this obviously this S1 and S2 are complementary. So this is known as chopper cell or off-bridge cell. Chopper cell or off-bridge cell or off-bridge unit. Right. So these chopper cells are connected. This is one chopper cell and another one. So these are connected. This is series connection, right? So this is connection. These chopper cells are connected. So like this. Right. So now let us assume that we'll discuss polarity generator later. So this is the point. So where it is connected to the polarity generator. Okay. So let us assume that it is having three cells. So it is energized with VDC1. So this is VDC2 and this is VDC3. Right. So if you notice that, so this one will produce, assume that all are VDC. So this one will produce VDC0. So this is producing VDC0 and this is also producing VDC0. So it can't produce negative levels, right? Because of this chopper cell, it will not produce negative levels. Off bridge will not produce negative levels, but full bridge or full H bridge will produce negative levels. That means it is a full H bridge if you have positive voltage, negative voltage and 0 voltage. Okay, right. So now I want 3 VDC across these 2 points. So which switches we need to turn on? If I want 3 VDC across, this is 1 for example, this is 2. If you want 3 VDC across 1 and 2, so which switches we need to turn on?
S1, S2, S3.
Right? So we need to turn on this switch S1. It will be like this. It will be like this. It will be like this, right? So all the 3 DC sources in series so that you can get 3 VDC level. Clear? So if you want only VDC sorry, two VDC. So which switches we can turn on? If you want two VDC, so that means one DC source we need to bypass, right? So when you turn on this switch or this switch or this switch, this source will be bypassed. The corresponding source will be bypassed, right? If you turn on S1 dash, this VDC1 will be bypassed. Similarly, if you turn on S2 dash, this VDC2 will be bypassed, right? So we need to bypass one DC source. Let us assume that this is something like this. It will go like this. It will be like this. So now we bypassed the third source, that is VDC3. Now we bypassed. Okay, clear? So this is to obtain 2 VDC. So there is another path. So not only this one, so there is another path. You can go like this. So this is another path, right? So this is also giving 2 VDC. So this is also giving 2 VDC. Now we bypassed this first DC source. So we have another path. So now we bypassed the middle DC source. Now we bypassed the middle DC source, right? So that means to obtain 2 VDC, you have 3 paths. So one with operating 1 and 2, operating 2 and 3, or operating 3 and 1. You can get 2 VDC. Similarly, to obtain VDC, if you want only VDC, so which switches we need to turn on? So something like this, right? We need to operate so this S1, S2 dash and S3 dash, or we need to operate this one, or operate the second cell, or operate the third cell. Clear? So that we can get VDC. So how to get 0 voltage? How to get 0 voltage? How to get 0 voltage across 1 and 2?
S1 dash, S2 dash, S3 dash.
So we need to turn on all these 3 switches, right? If you turn on all these 3 switches, all the DC sources are bypassed, so that you can get 0 voltage. Okay, so that's why it is known as level generator. So you are getting a 3 VDC level, 2 VDC level, VDC level and 0 level. Clear? So that means the levels will be something like this. So you have, this is all are positive, okay, like this. So this is VDC, 2 VDC and this is 3 VDC. Clear? So now right, so now come to this polarity generator. So this is a simple H bridge, right? So this is simple H bridge, right? So normally if you give a DC source to an H bridge, right? So that will convert, you know that basic operation of H bridge, right? So if you give a DC source, if the input is a DC source, the output we can make this to a pulsating DC, or we can make it to a AC waveform, right? Like this. So in positive half cycle, you divide the time period into 2 parts. Half of the period, so we'll trigger this H1 and H2 dash. Half of the period we need to trigger this H1 and H2 dash, or H3 and H1 dash. So remaining half of the period, we need to operate the other opposite switches, right? We need to operate these switches. So we need to operate these switches to obtain positive levels, and we need to operate these switches to obtain negative levels. So that is basic principle of H bridge, right? So that is how an H bridge will work to obtain a AC waveform, right? So now the input for this H bridge is this is the input, right? So the input for this H bridge is this kind of waveform, right? So this kind of unipolar waveform. So this unipolar waveform we need to convert into bipolar. That means positive half cycle and negative half cycle. So how it is working is, right? So in every cycle, the cycle is divided into 2 parts. Half of the period we need to get a positive half cycle, and the remaining half we need to get a negative half cycle, right? So for positive half cycle, we need to trigger so this H2 and H1 dash switches. If you trigger this H2 and H1 dash signal, so in that case you can get a positive half cycle, right? And if you trigger this H1, the H1 and H2 dash, you can get a negative off cycle. Whatever this input is there, right? So that will be flipped, right? So that you can get a negative off cycle. So that's why it is known as polarity generator, and this one is known as level generator. So one part is producing the levels and the other part is producing, or the other part is making positive off cycle and negative off cycle, something like this. So this is the output of level generator. So this is the output of level generator, and this is the output of polarity generator. So this is the output for the polarity generator. So from up to here, so this switches S2 and H1 dash here, H2 and H1 dash are operating. So here H1 and H2 dash are operating, so that you're getting a negative voltage across A and 0. This is clear? So that's why it is known as level and polarity generator. So one is producing unipolar levels and other converting that levels into positive off cycle and negative off cycle. Right? Clear? So now, right? So how many levels you will get if you assume that all are equal sources? So this is VDC, this is VDC, and this is VDC. So that means you will get VDC, 2 VDC, VDC, and 0. Right? After polarity generator, you may get minus VDC, minus 2 VDC, and minus 3 VDC. So that means you can get 7 levels with 3 DC sources. You can get 7 level with 3 DC sources. In the phase voltage, right? So in case, if you, this is for single phase. If you want to go for 3 phase, if you want to go this one for 3 phase, so this is for A phase. Similarly, the same structure for B phase and another structure for C phase. Okay, so this entire structure is for A phase. If you want, we have B phase and C phase. All these 0 points are there, right? So all are connected together like an H bridge. In H bridge, we are connecting all those points, right? So similarly here also we need to connect all these zeros. So this is 0, if you have another 0, right? So these zeros must be connected. So this is A phase 0 and this is B phase 0. So all these zeros must be connected, right? So here you have A phase, B phase, C phase. So likewise we have 3 phase. So if you have equal DC sources, it can obtain 7 levels in the phase voltage and 13 levels in the line voltage, right? 13 levels in the line voltage. And another thing is, it will work with asymmetrical also, right? If you have 1:2, 2:3, for example, so this 1:2:3 DC voltage ratio. So in that case, so how many levels you can get? It is 1:2:3. So what is the maximum voltage across this one you can get? What is the maximum voltage across this you can get?
6 times
6 VDC.
6 VDC, right? So how many levels you can get? So it is varying from 6 VDC to minus 6 VDC. So that means you can get 13 levels. You can get 13 levels. Right, and it also work with, this is we have different asymmetries are there, right? We have this arithmetic progression, geometric progression with binary and trinary ratios. We already discussed this, right? So that it supports arithmetic progression, that is 1:2:3. So this one it will support, and it will also support, so 1:2:4. Okay, it will also support 1:2:4. So how many levels you can get? 1:2:4. So that means 7 VDC, right? It will varying from 7 VDC to minus 7 VDC. So that means you can get 15 levels, starting from plus 7 VDC to minus 7 VDC. Right? But it will not support 1:3:9. It will not support 1:3:9. So why? Why it will not support this trinary voltage ratios?
we
Why?
can't get to it.
Right. We already discussed that. So whenever a trinary ratio, if it is supports, so each basic unit, this is one basic unit, or this is another unit, and this another unit, right? So each unit must produce, right? Each unit must produce positive voltage and negative voltage. So then only we can add and subtract, right? So here only addition is possible, but no subtraction, right? Here this output and this output we can combine, but we cannot differentiate the voltages, right? We cannot differentiate the voltages. So then if you are not differentiating the voltages, it will not work with trinary voltage ratios. Okay, if you want only two levels or 2 VDC, in that case, so this will be operate with plus 3 VDC and it will operate with minus VDC, right? So that means you will not get 2 VDC. So that is only possible if each unit will produce both positive and negative voltages. In case of CH bridge, so it will generate both positive and negative voltage along with 0, right? So that means we can easily add, and so that means additive combinations and subtractive combinations. So both it can support. So in that case, only the trinary voltage ratio works. So here this it won't work. Okay. So this is about the asymmetry in case of this topology. So come to its blocking voltage. So what is the blocking voltage of each switch? We already discussed it, right? So blocking voltage means, so whenever the switch is not conducting, the peak voltage across the switch is the blocking voltage. So what is its blocking voltage? Each switch S1, S2, S1 dash. What is the blocking voltage?
VDC.
Yes, its blocking voltage is equal to this DC source, right? Its blocking voltage is equal to this DC. See, this point is clamped here, and this point is also clamped, right? So this point is connected here, this is connected here, right? So we have two options. So when S1 is conducting, right, the voltage across this S1 dash is VDC1. Similarly, when S1 dash is conducting, the voltage across this S1 is VDC1. Okay, so that means these switches must be rated for VDC1. Similarly, these switches must be rated for
VDC2.
VDC2, right? So these switches must be rated for VDC3. Clear? So these are rated for VDC1, VDC2, or in other words, so here each cell, whatever the voltage, so that is connected, so that switches must be rated for that voltage. Okay. So now, what is the blocking voltage for this switch? What is the blocking voltage for this switch?
Half of VDC1 plus
VDC1 plus VDC2.
See,
Sum
what is
of
the
all
see here? What is the input for this H bridge? So this is the input, right? So what is the input peak value? That is VDC1 plus VDC2 plus VDC3, right? Okay. So that means each one, right? So each one, for example, these two only will conduct, right? For example, these two one conduct. So what is the voltage across this one? What is the voltage across this switch S2? What is the peak voltage across this H2? If H1 and H2 dash are conducting, so what is the peak voltage across this H2?
Sir, if they are conducting, then no voltage will be
VA
across.
not sir, total voltage.
No, see here, for example, so this is conducting, right? So here this is conducting, that means the H2 and so H1 dash are conducting, right? Okay, so this H2 and H1 dash, oh sorry, these are conducting. So what is the voltage across this switch? So this voltage will appear as a blocking voltage, right? For the switch is conducting, so in that case the source voltage is appeared across here, right? Agree? If S1 is conducting, the source voltage appear across the switch, right? Similarly, this is conducting, right? So whatever this entire voltage, so that will be appeared across this non-conducting switch. If the switch is conducting, its voltage is 0. If it is not conducting, right, the voltage across that source, this means this voltage will be appeared across the H1. So what is the peak voltage that will be? So this is the peak voltage, right? So that means the voltage that is VDC1 plus VDC2 plus VDC3. So that is the blocking voltage for each switch, H1, H2, and all four switches. Clear? The total blocking voltage for polarity generator is equal to VDC1 plus VDC2 plus VDC3, or how many, if it is VDC4, so that VDC4 is also included. Clear? And the interesting thing is, so what is the switching frequency of this each switch? These switches, if you observe that, so these are operating in PW mode. Okay, these are operating in PW. You can see that PW mode, right? So these are operating in PW mode. But whereas the switches in polarity generator, so they are operating in fundamental frequency. They are operating at fundamental frequency, right? So in each cycle, during positive half cycle, so this H2 and H1 dash are conducting continuously. So during negative half cycle, this H1 and H2 dash are conducting. So that means here this entire this H1, H2 and H1 dash are on. So here H1 and H2 dash are on. Okay. So here these switches, these level generator switches are operating in PW mode, whereas polarity generator switches are operating at a fundamental frequency. So that means this loss, even though they are rated for large voltage, but they are operating at low frequency. So that is one advantage. So with this circuit. So another advantage is, if you want to increase the number of levels, you can add another H bridge like this. I can slightly change these H bridge cells so that the levels can be increased. If you want to increase, you just add one more block here so that the levels can be increased. So these are some merits. So one is the modular and redundant structure. You have seen the switching redundancy is right. If you want 2 VDC or VDC level, you have multiple options are there. So this is H bridge configuration. So this can be generalized. This topology can be generalized to any number of topologies. It has separate polarity and level generator. So even power distribution and equal utilization of DC sources are possible. So in this, like CHB, by using an appropriate PW method, we can equate all this power delivered by all these DC sources into equal. So we can natural balancing of this DC capacitors. When this power delivery is equal, so then we can obtain a natural balancing of this DC sources or this capacitor if you replace with. So equal device blocking voltages in level generator, so that we discussed, right? Level generator switches, right? If we assume that the DC sources are equal, the blocking voltages, all these switches are equal, and it can produce a voltage for additive combination of DC source. We already discussed that it will produce only for additive combination, so not for subtractive combination. So it is partially fault tolerant. So this topology is partially fault tolerant. So meaning is, right? So meaning is, for example, this cell is faulty. For example, this cell is faulty or this DC source is faulty. We can bypass this DC source, right? We can bypass this DC source. For example, this DC source is faulty. You can bypass this DC source by turning on this switch. If you turn on this S1 dash, this DC source will be bypassed. Okay, so now we can operate with two cells. But we said that it is a partial fault tolerant, right? So why it is partial fault tolerant? For example, we have faults in this H bridge, right? For example, this H1 is faulty. So in that case, you can obtain only positive levels, right? You can obtain only positive levels, because this one will convert these positive levels into negative levels, right? If this is not working, you can generate only positive levels. Okay, it can generate only positive levels or only negative levels, right? So that means you can generate only one off, means only one positive cycles, and remaining off, that means here you see this diagram. For example, this is faulty, right? So that means it will generate only positive half cycle. This negative half cycle it won't generate, right? Because this is H1 is faulty. in the next half cycle it will also generate another positive half cycle. So that means, so whenever there is a fault in this polarity generator, we cannot reconfigure the inverter, but when you have faults in this level generator, so in that case we can reconfigure the inverter. So that is the main thing in this multi-level DC link. So this is the switching table I have given for so this is level generator here, polarity generator. So which switches we are operating, right? So at any time we are operating only 3 switches. Okay, we are operating 3 switches at any time, and in polarity generator we are operating 2 switches. For positive half cycle we need to operate H1 H2 dash, something like this. So we need to operate these 2 switches, and this is for equal voltage ratios, and this is for if the voltages are in 1:2:3. If you notice that, so some redundancy is there. If you are operating with equal voltage ratios, we have some redundancy, or if you have operating with 1:2:3 ratio, the redundancy will be reduced. See, we have redundancy for -3 VDC and -3 VDC, right? So here you have -2 VDC, -2 VDC, -2 VDC. We have 3 switching instants are there for -2 VDC, whereas here for -3 VDC you have only 2. For -2 VDC, I think you have only 1 switching instant is there. So this is about some multi-level DC link. So next one is switched series parallel sources. So that is SSPS, switched series parallel sources. So this is also based on separate level and polarity generator based structure. So here the polarity generator, the operation is same, whatever we discussed earlier, right? So that is same. Here the level generator is different. The level generator is different. So it is structured something like this. It is energized with VDC1. So we have this VDC2 and we have this VDC3. So now if you want to operate these 3 DC sources in series, so which switches you need to trigger? If you want to operate these 3 DC sources in series, so which switches you need to trigger?
S2 and S5.
S5.
Yeah, if you turn on this S2, it will be like this, right? So it will
Yes,
be like this, right? If you turn on this, so it will be like this. Agree? So all the switches will be, means all the DC sources are turned on, right? So now if you want to produce 2 VDC across these 1 and 2, so which device you need to trigger?
S2, S6.
2 VDC, S2 and S6, yeah.
S6.
S2 and S6. If you turn on S2 and S6, you can obtain 2 VDC, right? Or else you can turn on like this also, right? You can turn on so like this also to obtain 2 VDC, or you can turn on like this also to obtain 2 VDC. Okay, so here also some asymmetry, some redundancy is there, but thing is that, so here turning on only 2 switches, you're turning on S1 and S5. So earlier case, if you notice that we need to turn on 3 switches at any time, right? So but here you are turning on only 2 switches, S1 and S5 you are only turning on. Okay, to obtain 3 VDC also you need to turn on only 2 switches. So these 2 switches we are turned on, right? S2 and S5 we turn on to obtain 3 VDC. Similarly, if you want only 1 VDC, you can turn on this switch, right? How to bypass that? So this is to bypass to these two DC sources, right? So here we need to turn on, we'll go like this. This is for VDC, and for if you want this one, it will go like this. If you want to operate only this one, it will be like this. But at any instant, right? So you need to turn on only two switches, S1, S4. Here in this instant, you're turning on only S1 and S4 to obtain VDC voltage, right? So, but if you notice that, so its name is switched series parallel sources, switched series parallel sources. So why it is called like this, right? So why it is called like this, right? If you want VDC level, for example, if you want VDC level, either you can operate this one, or this one. We have three options are there. You can operate this one, or this one, or this one. So that means one is feeding, right? So but we have option, right? We have option so that these three DC sources we can connect parallelly. These three DC sources we can connect parallelly. So something like this. So this is 1, 2, and 3. If you want this thing, right? If you want to connect these three DC sources in parallel, so which switch we need to turn on? So which switches we need to turn on?
Sir, we will turn on all the switches except S2 and S5.
Yeah. If you turn on this, right? So this is negative. It's negative, right? So we need to connect this negative here to this side. So that means we need to turn on the switch S1. Similarly, if you turn on this S4, so this point is connected here, right? All the negatives are connected. All the switch negatives are connected, right? If you turn on S1 and S4, the negatives of the DC sources are connected together. Similarly, if you turn on this S3 and S5, if you turn on this S3 and S5, the positive plates are also connected, right? If you turn on this S3, the positive plate is connected. If you turn on this S6, this positive plate is connected here, right? Same thing here, connected here like this. So that means positive and negative plates are connected in parallel. So that means you can get this. So now if you want VDC, right? If you want VDC level, so all the three DC sources are feeding the load. All the three DC sources are equally feeding the load. That means this is off of the 1/3 of the current it is giving, and it is giving 1/3 of the current, and it is giving 1/3 of the current. Okay. So that is the advantage with this circuit. So where this advantage useful is, here we can replace these inner ones with these capacitors. So you will keep one stiff DC source here. We have one stiff DC source. That means you have one DC source. We can replace this one with capacitors. Here also we can replace this with capacitors. Okay. So now all these capacitors we need to recharge, or we need to charge it to VDC, right? So if this is VDC, if we want to charge this to VDC. Here also we want to charge to VDC. So how to charge that? How to charge this capacitor to VDC at initial stage? So we need to turn on the switch S1 and S4. Similarly, we need to turn on this S3 and S6, so that all these things, now these things will replace with capacitors. Okay, one DC source and two capacitors are connected in parallel, so that these capacitors are charged to the source voltage. Right? These capacitors are charged to this source voltage. So now what will happen? If this capacitor is charged to source voltage, so now it will act as a source. So this capacitor is acting as a source. So whenever, if you notice that in this capacitor voltage is reduced, right, in when you are obtaining this VDC voltage levels, again we are switching on this S1, S4 and S3, S6, so that again these capacitors are come in parallel with the DC source, and its charge will be maintained. It's clear? It's clear. So we can replace these with capacitors. We can replace with capacitors, and now we can operate with only one DC source. We can operate with only one DC source. So whenever if it is a capacitor, obviously at some point of time this voltage will be reduced. For example, if you are operating with 3 VDC, for example, you are operating with 3 VDC, assume this is 100. So initially this is also 100, this is also 100, right? If you want 3 VDC, 300 voltage, you need to turn on all the switches. So that means all the three sources we need to turn on, right? So now we are getting 300 volts, and this 300 volts is feeding the load. So when it is happening, so in that case, this voltage will be slightly reduced, right? Assume that this voltage is reduced to 97 volts. assume that this voltage is reduced to 97 volts. But when you are obtaining VDC level, again, if you want VDC level, we need to turn on this S1, S4, S3 and S4. So in that case, all the DC sources will come into parallel, right? With the DC source, all the capacitor will comes in parallel with this DC source, right? So now this capacitor voltage is increased to 100 volts, and this is voltage also increased to 100 volts. So that means this capacitor we can maintain, that means self-balanced. So this capacitor voltage will be reduced when they are feeding the load, but when they are coming parallel to the DC source to obtain some certain levels, so in that case these capacitors will be self-charged. Right, these capacitors can be self-charged. Whatever that voltage lost in the capacitors, again it is charging from the stiff DC source. You can operate with 2 VDC also. If you want to operate 2 VDC, we can make these two in parallel along with in series. You can operate that. Okay. If you want 2 VDC, you can make these two in series along with, you can make these two in parallel and make the two series with this. You can operate. So likewise also to obtain 2 VDC level. So this is about the switched series parallel sources. Right. So here, if you want to increase the number of levels, you can easily increase that. The polarity generator, whatever we discussed for MLDCL, the same applies here also. The blocking voltage of each switch is equal to this H1 is equal to the sum of the DC sources. So whereas here its blocking voltage is VDC1 and its blocking voltage is VDC2 and its blocking voltage is VDC3. Okay. So it will also support asymmetry. It will also support asymmetry, but it will not support 1:3:9 ratio. It will not support 1:3:9 ratio because it will not produce because the output voltage only for additive combination of DC sources. So therefore, it will not produce asymmetry. Equal DC balancing voltage, it is possible. So voltage boosting ability. So we already discussed, right? What is voltage boosting ability? With one DC source, with VDC DC source, you can obtain actually with one DC source, you can obtain 7 levels. So in this particular case, you can get 7 levels, right? But we are operating with only one VDC. So from this, we can define voltage gain. So especially in this capacitor, when DC sources and capacitors are involved, so we can define voltage gain. So voltage gain is defined as maximum output voltage by sum of stiff DC source present in the inverter. Maximum output voltage by sum of the stiff DC source present in the inverter. So in this particular case, right, so what is the voltage gain? What is the voltage gain? If you are replacing this VDC2 and VDC3 with capacitors?
3.
3, right? So the maximum voltage you can obtain this A and 0 is, it is varying from plus 3 VDC to minus 3 VDC, but you have only source of VDC. So from this, so maximum output by sum of the stiff DC source output, right? We have only one stiff DC source. So that's why it is 3 VDC by VDC. That means the voltage gain is 3. So that means you are getting here 100 volts if you are giving here. On the output side, you are getting 300 to minus 300 volts output. Okay. So that is voltage gain. So that is only if you are replacing with some of the DC sources with capacitors. So that only that will comes into the picture. In normal case, if this is not DC source, for example, in this case, the voltage gain is always 1. Okay. The voltage gain is always 1 only. Right. So we have another one. So that is total standing voltage. Total standing voltage. Right. So that is how it is defined as the maximum or the sum of the blocking voltage of all switches is known as total standing voltage, sum of blocking voltages of all switches. Sum of blocking voltages of all switches is known as total standing voltage, right, or total blocking voltage, or total blocking voltage. So in this particular case, if you assume that, so VDC1 equal to VDC2 equal to VDC3 equal to VDC, for example, this is VDC, so this is also VDC, and this is also VDC. So what is its total standing voltage with this topology? What is the total standing voltage?
6 VDC.
Total standing voltage means it is included for all the switching devices, right? So this one, these two switches, I will erase here. So these two switches, what is this blocking voltage? This is VDC, right? So this is also VDC, this is VDC, this is VDC, this is VDC, right? The total is 6 VDC. Agree? In level generator, it is 6 VDC, right? Agree?
Yes, sir.
In coming to this polarity generator, so this is 3 VDC, this is 3 VDC, this is 3 VDC, and this is 3 VDC. So that means 12 VDC. So that means its total blocking voltage is 18 VDC. Its total blocking voltage is 18 VDC, or total standing voltage TSV is 18 VDC. Clear? So this is how we will find out the total standing voltage. We have the total standing voltage in some papers, they will mention per unit form, total standing voltage in per unit form. So what is the formula for that? The total standing voltage divided by sum of, right, sum of total DC voltage, sum of total DC voltage. So in this particular case, so this is 18 VDC, sum of the DC source voltages are, so this is VDC1, VDC, 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 right? So that is 3 VDC. So that is 6 is its total standing voltage in per unit form. Clear? So 18 VDC by sum of the DC sources, so that is 3 VDC. So 18 by 3, so 6 is its per unit total standing voltage. Hope it's clear. To calculate the
Sir,
total
what is
standing voltage, you need to calculate the blocking voltage for each switch, and we need to add all. Okay, if you want that per unit form, the total standing voltage, whatever you obtained by total sum of the stiff DC, or not stiff, all DC sources here, all DC sources. So that gives you the total standing voltage in per unit form. Okay, so this is the switching table. So the advantage here when compared to this MLDCL, so only one switch is conducting, only one switch is conducting, only one switch we are conducting. So here there is a drawback, right? So there is a drawback in this level generator. So what is the drawback is, so this level generator will not produce zero voltage. See, you cannot obtain a zero path for here. So in this level generator, you cannot obtain a zero voltage path. Right? If you want zero voltage path, you have to operate something like this. But if when you are operating this S4 and S5 switches, what will happen? This source is short circuited. So you cannot obtain a zero voltage path here, right? For obtaining the zero voltage can be obtained by from this level generator. Operating these two switches or operating these two switches, the zero voltage can be obtained. So here this will produce 3 VDC, 2 VDC, VDC only, that it will not produce zero, but that zero is obtained from this polarity generator. So whereas here, so in this source or in this circuit, right, you can obtain zero voltage by operating these three switches, right? By operating these three switches, you can obtain zero voltage. So here also, if you want, you can operate these two switches or these two bottom switches to obtain zero voltage. It's clear? So that's why for 0 voltage, so some dots are given, so that means there is no path for that, so only it can be obtained from the polarity generator. So next one is the reverse voltage. This is another topology, RV topology, reverse voltage topology, right? So here the circuit is like this, the polarity generator, so its operation is also same, that means whatever we discussed earlier, the same stands here. Okay, so this is one cell, this is another one, and this is another one. So here each one, so here also each one producing VDC, this is also VDC and this is also VDC. But if you want to increase that levels, we need to duplicate this encircled, we need to duplicate this encircled portion. If you want to duplicate that, so we need to encircle this duplicate, this one, we need to add another unit here, another unit, something like this, so that it can be increased to higher levels, right? So come to its thing. So if you want to operate these 3 DC sources, the path will be something like this, right? So we need to turn on the switches S1 and S6. If you turn on S1 and S6, all the 3 DC sources will come in parallel, so in series. If you want to operate only 2 DC sources, so that means it may be something like this. You can go like this. If you want only 2 DC sources, this is one way, or you can also go like this. Okay, you can also go like this, right, by bypassing this is S6, right? Similarly, if you want 0 voltage, which switch we need to trigger? To obtain 0 voltage, so which switch we need to trigger?
S2, S3, S5.
Yeah, these 3 switches, right? This S3, S2, S5, if you trigger, the voltage will be 0. Okay, right? So this is about the reverse voltage topology. This is about this reverse voltage topology. If you want to increase that, we need to increase this encircle portion, right? So now the question is, right? So now the question is, what is the blocking voltage for this switch S6? What is the blocking voltage for this switch S6?
VDC1 plus VDC2 plus VDC3.
VDC1 plus VDC2 plus VDC3. It's right. So I will show you. For example, you are getting a 0 voltage level. So this is to get a 0 voltage, right? Agree? This is to get a 0 voltage, right? So now what is the blocking voltage for this S6? What is the blocking voltage for this switch S6?
Sum of all sources.
By sum of all sources, this is not connected, right? This switch is not
2
conducting.
VDC.
This switch is not conducting, right? So what is the blocking voltage? So here you can see that, right? This point is, right? This is now off, right? So this is point is here. So that means this point is here and this point is here, right? Agree? If this is A, so this is also A, right? Agree?
Yes, sir.
Okay, because
Yes,
it is
yes.
connected, right? So now, so this is another point, right? What is the voltage across? If we assume this is B, what is the voltage across A and B?
VDC2 plus VDC3.
VDC2 plus VDC3. VDC2 plus VDC3, right? So that means the switch S6 is supposed to block VDC2 plus VDC3, right? Similarly, this switch S1, how much voltage this switch S1 is supposed to block here?
VDC1.
Only VDC1, because this point is clamped here, right? This is only VDC1. So this is for one case. So let us assume that it will be like this. So what is the blocking voltage for switch S6? So in this particular case, what is the blocking voltage for switch S6?
VDC3.
Only VDC3, right? So only VDC3 its blocking voltage. Okay. So what you notice that the blocking voltage for all these switches are unequal. So especially these two switches. So this switch and this switch. So here this switch is always blocking voltage is equal to VDC, right? Because this point is clamped here. This point is clamped, right? So its blocking voltage S3, S6 blocking voltage will be, if S3 is on, but we have two options. For example, this S3 and S4, this is on, right? So this is off, its voltage is VDC. If this is on, so this is off, its voltage is always VDC. That means that for duplicating unit, its voltage blocking is always equal to that VDC. But this one will always changes. So this one will always changes, right? So this is equal to VDC2 plus VDC3 or VDC1 plus so VDC2. So that's why it is having unequal device blocking voltages. Earlier in level generator, the blocking voltages for all devices are same in case of symmetrical. So here the blocking voltages are not same. So this switch will be rated for different thing, and these switches are rated for different, and these switches are rated for different values. So that is the drawback with this method or with this topology. So this is also same thing, whatever the features we discussed, right? It will also support for symmetrical and asymmetrical, but it will support only for, it will not support for trinary voltage ratios. So next one, this is series connected switched sources, SCSS, series connected switch sources. So this is for 7-level topology. This is for 7-level topology. So if you want to operate all the 3 DC sources in series, so which switches you need to trigger? Which switches we need to trigger if you want to operate all these 3 DC sources in series? Which switches we need to trigger?
S1, S3, S5.
So this S1, S3, S5 we need to trigger, right? So we need to trigger these 3 DC sources to obtain this VDC1 plus VDC2 plus VDC3. If you want only VDC2 or VDC2, which switches we need to trigger? 2 VDC, which switches we need to trigger?
S2, S3, S5.
Yeah, S2, S3, S5. Similarly, VDC,
S4, S5.
S4, S5 we need to trigger, right? S4, S5 we need to trigger. Okay, only 2 switches we need to trigger. If you want 0 voltage, we need to trigger this S6, right? If you want 0 voltage, we need to trigger this S6, so that this will be the path. It requires least number of switches. If we compare that, it requires only 6 switches, right? But there is a drawback here. So what is the blocking voltage of this S2, S1 and S2? What is the blocking voltage of this S1 and S2? What is the blocking voltage for the S1 and S2? We already discussed it, right?
VDC.
This is on, this is the blocking voltage. Its blocking voltage is VDC1 only. If S1 is on, S2 is on. So this is the blocking voltage. So that means the blocking voltage of this switch S2 is VDC1. So what is the blocking voltage of this S4? What is the blocking
VDC1
voltage?
plus VDC2.
VDC1 plus
VDC1 plus
VDC2.
VDC2, right? If it is something like this is the operation. So in that case, this point is clamped here. This point is also connected here, right? That means 2 DC sources are comes into series. That means this is blocking for sum of 2 DC sources. Similarly, this S6, This switch S6.
Sir, 1 plus 2 plus 3.
1 plus 2 plus 3. That means this is for VDC, this is for 2 VDC, and this is for 3 VDC. So if you have only one, that means you have to connect another device here. You have to connect 3 more devices here. Okay. So that is the drawback. So with this topology, so blocking voltages are unequal. So in this particular case, what is the total standing voltage? Total standing voltage. So what is the total standing voltage for this particular case?
8 pu.
You can calculate, right? So for these 3 switches, the total standing voltage is 12 VDC, right? So for this is you can I think you're not. So what is the blocking voltage of this switch S3? S1 is already calculated, right? So S1 is already this, right? What is the blocking voltage of that switch S3? S3 and S5? So what is its blocking voltage?
VDC 1.
What is the blocking voltage of the switch? So here the block, see here, this is the case, right? Okay, this is the one, right? So what is the blocking voltage for that particular switch?
Yes, sir. VDC 1 plus VDC 2.
So this is not on, right? So this is not on. Switch is off. The switch is also off,
VDC.
right? Only VDC, right? So these switches are only VDC because it is connected between 2 DC sources, right? Therefore its voltage is always VDC. The switch voltage is always VDC. So that means this is VDC. So this is VDC and this is also VDC. So this is VDC and this is 2 VDC and this is 3 VDC. So here all are 3 VDC. So what is its block in total standing voltage? If we add all, so 3 VDC, 6 VDC, 9 VDC plus 12 VDC. I think around 21 VDC. Correct? Is correct?
Yes, sir.
Okay. The total standing voltage is 21 VDC. If it is in per unit form, so it will be 21 VDC divided by this 3 VDC, right? It will be 7. Right. So this is about the series connected switch sources. So this is another one. This is another one. So multi-level module. So multi-level module. This is also known as MLM. Right. Another drawback with this one is it will not support asymmetry. So in this, it will not support asymmetry. This topology, this series connected switch sources, right? It is not supports asymmetry. It will, so it must be symmetrical. So whereas here, so this is bidirectional switches are connected here. We'll discuss what is bidirectional switches. I hope already we discussed this. If you want to add 3, this will be the path. If you want to add all the DC sources, 3 DC sources, so that will be the path. If you want only one, so we need to operate. We need to operate like this, right? Or we need to operate like this. Clear? If you want only VDC, it will be the path. If you want 2 VDC, it will be the path. If you want to operate all 3, so it will be the path. Okay. So here these bidirectional switches are used. Okay, we'll discuss in the next class. It will take time. So here bidirectional switches are, right? We already discussed that these bidirectional switches we discussed, right? I hope it is in common emitter. We have discussed this.
Yes, sir.
We are already discussed.
Yes,
I
sir.
think only one chord. I think this is in common emitter form, so that only one gate driver is required. One gate driver is required for this. So that is the advantage. And moreover, only one switch is conducting, right? So here, for example, if you want 3 VDC, for example, right? So only one switch is conducting. That means either this diode will conduct or this switch will conduct, or this diode will conduct or this switch is conducting. So that means only one switch is conducting to obtain any voltage level. So only one switch is conducting. So that is the advantage with this. For example, if this is the voltage level, right, only one switch is conducting, right? In these two switches, one diode, and in this, if it is diode is conducting here this this switch is conducting. So therefore only one switch is conducting. So in this case, so that is the advantage with this. And the drawback is it has for example, voltage drop is very high. For example, if this is the operating, I'm operating with 0 voltage level. So what is the voltage blocking of switch S1? What is the blocking voltage of switch S1? This is for 0 voltage level, right? So what is the blocking voltage for switch S1?
VDC1 plus VDC2 plus VDC3.
Yeah, so this point is connected here, right? So here the other point is connected here. Okay, this is on, so that means this is entire thing is on. That means this is connected here. So this point is connected, meaning that means the blocking voltage is VDC1 plus VDC2 plus VDC3. So this entire thing or two devices will share VDC1 plus VDC2 plus VDC3. That means each one will be share half of this voltage. That means the diode will share half of the voltage, and the switch will, here only this diode is and this switch is conducting, or this diode and this switch is conducting, right? So that means each one will share half of this voltage, because these two are connected in series, right? So that means each one will share half of this voltage. So that is the drawback. Similarly, if you are operating with, this is the voltage, right? If this is the case, so what is the blocking voltage of this switch S4? What is the blocking voltage of this switch S4?
VDC1 plus VDC plus VDC3.
VDC, again this is VDC1 plus VDC2 plus, so VDC3, right? Okay, so that is the blocking voltage of that switches. And what is the blocking voltage of this S3? What is the blocking voltage for S3?
Sir, VDC1 plus VDC2.
No, see this S3 is there, right? So this point is clamped here. Okay, if this is not conducting, so this voltage is always VDC2, right? Okay, so this voltage is always VDC2. This point is, this is simple H bridge, right? That what we discussed. So this point is clamped here. So it may not, if this is conducting or this is conducting. This is conducting, this voltage is VDC. If this is conducting, this voltage is VDC, right? So that means this point is always VDC2. Its voltage is always VDC2. So that means the outer switches, so these switches are rated for 3 VDC. These outer switches are rated for 3 VDC, and these inner switches are rated for this VDC2, or in other words, these are rated for VDC. And another thing is, it will not support asymmetry. So whatever the sources, it must be same. The sources must be same. So this is about this multi-level module. The advantage with this multi-level module is only one switch is conducting, right? Only one switch is conducting, and this is the scenario, but there are several drawbacks are there. So usually this is not preferred. If you compare all these, whatever we discussed, right? So commonly used topologies, if you compare whatever we discussed, so this one is commonly used, so this is also preferred. So here SSPS, there are some drawbacks are there. So here also drawbacks are there. So this here also some drawbacks are there. So this is extension of this cross-connected. This topology is just an extension of this topology. So this topology is less not frequently used. So only this topology, this MLDCL and SSPS are the preferred choices. Okay. All this topology, this is having unequal voltages. So here also unequal voltages, here also unequal voltages. This circuit itself is complex. So among this is preferred, MLDCL is preferred and SSPS is also preferred. If you compare these two again, right, if you compare these two again, so in SSPS, there's certain advantage that you can replace these capacitors, or we can replace these DC sources with capacitor. And another one is only two devices are conducting. In case of these two, right, only two devices. If you have three DC sources, only two devices are conducting. So whereas here three devices are conducting, so that means the switching losses for this SSPS is slightly less. Okay, the switching losses, especially in the level generator. Polarity generator, anyway, both are same, right? Both are operating in the same, right? Polarity generator wise, both are same. But in the level generator, the switching losses are usually reduced by, here three switches are conducting, here two switches are conducting, right? So that means the reduces by 33% approximately. Reduces by 33% approximately, right? So that means these are MLDCL and SSPS are the preferred choices. Okay. You have any doubts? You can ask me now.